This is the second part of the lecture on ferromagnetic spin waves. Actually, in first part of the lecture on ferromagnetic spin waves, we have discussed the magnon dispersion relation in very detail. Okay, and now in today's lecture, we are going to see a very important concept of ferromagnetic spin waves, and this is regarding the thermal excitation of not thermal excitation but quantization of spin waves. Okay, actually in third part of the lecture we will see the thermal excitation of spin waves. Actually, you have learned that whenever a spin is excited, that excitement of a spin is not localized to that particular spin, but this excitation is shared by the whole system of the spin through exchange interaction, as you can see in this figure A. Okay, and therefore the excitations propagate through the system of a spin in a wave-like form, as you can see in this figure B, and this wave-like form is actually called spin waves, or when it is quantized, then you say these are magnons. Okay, actually you have learned that these are actually analogous to lattice vibration or phonons. In fact, spin waves are oscillations in the relative orientation of a spin on a lattice. As you know, the lattice vibration are oscillations in the relative positions of atoms on a lattice. Okay. So, as I have told you that the aim of today's lecture is to discuss the quantization of spin waves. So, how we can discuss this problem, let us now see. You know that if a ferromagnetic material is in its ground state, when you say ground state, that means the state of lowest energy. Probably such a state is such a state exists at 0 Kelvin temperature. So in ground state, actually the spin waves are not excited, and therefore all the spins are parallel. As you can see in this figure, I have shown that all the spins are parallel to one another. Okay, this is the situation when the ferromagnetic ground state is observed. Now, if you consider that S is equal to the value of each spin and N represents the total number of spins. Okay, so in ground state, what will be the total spin of this system? This will be simply equal to N times S, because you know spins are vectors, and when vectors are parallel to one another, the resultant vector is the magnitude of the resultant vector is simply equal to magnitude of the individual sum of the magnitude of individual vectors. So in this condition, the total spin will be simply equal to N times S. Okay, but what happens when the spin wave is excited? Any particular spin is excited, as you have learned that whenever you excite any particular spin, let us say we excite this particular spin, you have just seen that the excitation is not localized only to this spin, but this is propagated by the spin interaction among all the spins, and that propagate like a wave, which is called a spin wave. Okay, in fact, the excitation of a spin wave lowers the total spin. Why the total spin will lower? Because in this condition, you know, after excitation, all the spins will not remain parallel. So if all the spins are not parallel, definitely the resultant spin will decrease. Okay, because when vectors are parallel, resultant is its maximum value. So if you consider that there are spins like these orientations, then the resultant of these vectors will be definitely less than n times s. Okay, so we simply say that excitation of a spin wave lowers the total spin. Okay, and so the total value is reduced below this value n times s. Okay, now here we are going to develop two important results in this present lecture. So our present concern is, first of all, to find a relation between the amplitude of the spin wave and the reduction in the z component of the total spin. When we will obtain this relation, you will see that the spin wave or the magnons are quantized. So this first problem is related to the quantization of a spin wave. And after that, we will also see to find an expression for energy Ek when a spin wave k is excited. Okay, so actually we are going to discuss two important facts in this lecture. First one is actually called quantization. We have to obtain quantization condition for a spin wave, and the another problem is to find the energy of a spin wave when it is excited. Okay, so now let us see how we can deal this problem. So first of all, we are going to see the quantization condition of this spin wave. For this, you have to think what you have learned in the first part of the lecture. Actually, in first part of the lecture, when we have discussed the dispersion relation of a spin wave, then you have obtained the wave equation and you have written the plane wave solution. Although in that lecture, the plane wave solution we have written in exponential form, but when you will express the exponential in terms of its real and imaginary component, then if you will equate the you will take only the real part, then actually the solution of a spin wave are given like this. For s component of pth spin spx, which we will now just write sx. In fact, in first part of the lecture, we have considered a particular spin, pth spin. So we have written the x component of the pth spin as sp superscript x. Now, instead of this sp of spx, we will simply write sx. And the plane wave solution for the spin wave for x component can be written as u cos pka minus omega t. Here actually p represents the pth spin, k is the wave vector, and a is the lattice constant, and omega is the frequency of the wave. And similarly, the y component of a spin, that is spy, which will be now written as simply sy, that is given by u sine pka minus omega t. Okay. So this result you have seen in the first part of the lecture. Okay. Now from here you can see, if you will square sx and sy and sum, what will be your result? You can see sx square plus sy square will be simply equal to u square times cos square of pka minus omega t plus sine square of pka minus omega t. But this bracketed term will be equal to 1. So this is simply equal to u square. So sx square plus sy square is simply equal to u square. This u is the amplitude of the spin wave. Okay. Now, the resultant spin vector s can be written as the sum of the three components of this spin vector. If sx, sy and sz are the x, y and z component of a spin vector, then you can write that vector s is equal to sxi plus syj plus szk. Here ijk are the unit vectors in the x, y and z directions. Okay, and so the square of the modulus of s square, that will be simply equal to sx square plus sy square plus sz square. Okay, but let us see equation 1. The sum of sx square and sy square, this is simply equal to u square. So instead of the sum of these first two terms, we can write u square. So s square can be written as u square plus sz square. Okay, and therefore sz is equal to s square minus u square whole to the power half. Okay, now let us take this s square as a common factor. Since it is inside the square root, so when you will write it outside of the square root, you have to write s. Okay, and so this will be s times 1 minus u square over s square whole to the power half. Now, if you are talking about the small oscillation or small amplitudes, then definitely this u square over s square, this will be much smaller than 1. Okay, and you know from binomial expansion that this 1 minus x to the power n, this is almost equal to 1 minus nx if x is much smaller than 1. This is called first approximation. So here, under the consideration that amplitude is small, we can see this number u square over s square will be much smaller than 1, and so from first approximation you can write this as 1 minus u square over 2s square. Okay, and n, which is actually the total number of spin. If you will multiply this equation both sides by this n, what will be your result? So n times sz will be simply equal to ns times 1 minus u square over 2s square. And so this is simply ns times minus nu square over 2s. Okay, and from here we can see that ns minus nsz, this is equal to nu square over 2s. Okay, now actually the quantum theory allows only the integral value of s minus sz. S minus sz, only integral value of this s minus sz are allowed in accordance with quantum theory. So if n is the total number of spins and ns minus nk, where small nk is the z component of the total spin when a spin wave k is excited, then from this equation you can write that this nk is equal to what? This will be n uk square over 2s on the basis of this. Or you can say that uk square is equal to 2s nk over n. Okay, actually here this nk is actually the number of this is an integer, and it is just equal to the number of magnons of wave vector k, okay, which are excited actually. So you can see that this uk, which is actually the amplitude of the kth spin wave, and this is quantized because it is governed by the integer rule. Nk is integer, so you can say that the amplitude of this wave cannot have continuous value, but the amplitude will have discrete values in accordance with the value of nk. Nk will be equal to 1, 2, 3 and so on. These are positive integers. So the amplitude of a spin wave in accordance with this relation A1 is quantized because it has discrete values. And so this particular relation which I have mentioned in this equation A1 is called the quantization condition for a spin wave of amplitude UK. Okay. And now it is evident from here that the each magnon lowers the z component of the total spin by 1. This is a very remarkable fact. Due to each magnon, the z component of total spin is lowered by 1. So there are, let us for example, there are 1000 magnons. Then the z component of the total spin will be decreased, will be reduced 1000 times. Okay, not times, but 1000 unit. Okay, this is a very remarkable fact. Actually, when in the third lecture on this spin wave, we will discuss the thermal excitation of magnons. Then this fact will be used, that each magnon lowers the z component of total spin by 1. Okay, so this is all about the quantization of a spin wave. Now we are going to see the second concept of this lecture, which will be regarding the calculation of energy when a spin wave k is excited. Okay, so let us see how we can find the expression for energy Ek when a spin wave k is excited. Okay, actually, for finding the energy Ek when a spin wave k is excited, we consider the interaction energy between two spins. First is Sp and another spin is Sp plus 1. These are actually the two neighboring spins. So let us consider the interaction between these two spins. Actually, in the previous lecture, when we have discussed actually the problem of Heisenberg exchange interaction, then you have seen if two spins Sp and Sp plus 1 will be interacted, then the interaction energy will be what? Actually, the interaction energy is given by minus 2Je times Sp dot Sp plus 1. This is the interaction energy if you are consider that there is an interaction between the spins Sp and Sp plus 1. Okay. Now, as I have shown in this figure, you can see that this phi is the angle between these two spins. Then, in accordance with the definition of a scalar product of two vectors, you can write it minus 2Je times mod of Sp times mod of Sp plus 1, okay, times cos phi. But the magnitude of these two spin vectors are equal, or you can say that length of these two spin vectors are equal, although their directions are different. So as a vector they are different, but the modulus of Sp and Sp plus 1 will be equal, and that is equal to S, let us say. So in that condition, you can write that this interaction energy will be minus 2Je times S square, because this mod of Sp and mod of Sp plus 1 both are S, and cos phi. Okay. So this will be the interaction energy when the two spins Sp and Sp plus 1 will get interacted. Okay. So I have actually made this calculation here. You can see, to find the energy Ek when a spin k is excited, we consider the interaction energy between two spins Sp and Sp plus 1. And we know the interaction energy is then E equal to minus 2Je times Sp dot Sp plus 1. And that will be simply equal to E equal to minus 2je s square cos phi. Okay. Now see the geometry of this figure. Actually here this u represents the amplitude of the spin wave. Amplitude of this spin wave. Actually this in this figure I have shown the sketch relating the angle phi between two spin vectors sp and sp plus 1 to the spin wave amplitude u and the phase angle ka. This angle ka is the phase angle. Okay. And from the geometry of this figure we can find the how we can relate this angle phi to the phase angle ka. And for this let us see this figure. Actually if you consider that this point is A, okay, this point is B and this point is C, and then I have shown actually separately here for calculation, and let us draw a perpendicular AD. Okay, then you can see from the right angle triangle ABD you can write sine KA by 2. Actually this is the perpendicular bisector, so this angle will be now KA by 2 and this angle is also KA by 2. And so from the geometry of figure you can see this sine KA by 2 will be equal to BD divided by AB, but AB is equal to U. And when you will consider the triangle ACD, you can write sine KA by 2 equal to CD by U. So BD is equal to CD and that will be equal to simply 2 sine of KA by 2. Okay. And so what will be this BC? BC, this will be simply BD plus CD and both are equal to U sine of KA by 2. So BC will be equal to 2U sine KA by 2. Okay. Now again we can find the value of this BC from the geometry of figure, or you can see from the triangle BOC. I have shown here in that figure separately. Now again you will draw a perpendicular bisector, let us say OD. Okay, this angle is 90 and this angle is 90. Then this angle will be phi by 2 and this will be also phi by 2. So from this figure you can see that this BD and DC are same and that is equal to OB sine phi by 2 or OC sine phi by 2. But OB and OC, these are actually the length of the vectors SP and SP1 which is equal to S. So this is S sine phi by 2. Okay. And therefore when we will have to find BC, that will be BD plus DC and that will be 2 sine phi by 2. So you can see from this geometry of figure that BC once we have calculated is equal to 2U sine Ka by 2, and after that you have seen that this same BC is equal to 2 sine phi by 2. So we can equate these two values of BC. Okay. So I have written it here. You can see that from figure I have directly written it here, but how this result actually comes I have explained separately in these two figures. I think you have clearly understood. This is simple geometry. Okay. So 2U sine of Ka by 2 is equal to 2S sine of phi by 2. Okay. And now this 2 and this 2 will cancel out, and so sine phi by 2 is equal to U over S sine of Ka by 2. Okay. Now you know from trigonometry that cos phi is equal to 1 minus 2 sine square phi by 2. This is a well-known formula of trigonometry. And so instead of this sine square phi by 2, from here you can write this is U over S whole square times sine square of Ka by 2. Okay. So in this way we have expressed this cos phi in terms of the phase angle Ka. Okay. Now let us substitute this value of cos phi in equation 4 to find this interaction energy EE. And so you can see here that this is equal to this, this is cos phi. Okay, but this, what is this 2 sine square Ka by 2? You know that cos phi is equal to what? Cos, as a formula, write cos theta. Cos theta is equal to 1 minus 2 sine square theta by 2. Okay, and therefore if you will write sine square theta by 2, what is this? This is 1 minus cos theta by 2, and therefore 2 sine square theta by 2, this is equal to 1 minus cos theta. Okay, so see here, this is 2 times sine square of Ka by 2. So instead of 2 sine square of Ka by 2, we can write 1 minus cos Ka. This is also a standard formula of trigonometry. So finally we get cos phi equal to 1 minus u over s whole square times 1 minus cos of Ka. Now let us use this value of cos phi in this equation 4, where we have defined the interaction energy EE, which develops due to the interaction between the spin Sp and Sp plus 1. Okay, instead of this cos phi, we will write that expression. So EE is equal to minus 2 JES square times this much. This is instead of cos phi. 1 minus u over s whole square times 1 minus cos of Ka. Okay. Actually, this is the interaction energy when you consider the interaction between two spins. Okay. Now, if you consider there are total n spins, okay, then what will be the total interaction energy? We will simply multiply by this number n to this value to get the total interaction energy. So when you will multiply the RHS of this result by n, where n represents the number of spins, then the interaction energy EE will be equal to minus 2 JEN times s square times 1 minus u over s whole square minus whole square times 1 minus cos of Ka. Okay, and this is written as EE equal to minus 2 JEN s square plus 2 JEN u square times 1 minus cos Ka. This is a very remarkable result. If I will ask a question that if all the spins are actually parallel, it means the system is not excited. Then what will be the total energy of interaction? In that condition, you know, the total energy of interaction will be equal to minus 2 JE times N times S square. Okay. But here you can see after excitation, when we calculate the total interaction energy, then expression is minus 2 JEN S square plus this much. This extra term comes here. So why this extra term comes here? Actually, this extra term represents the excitation energy of the spin wave of amplitude UK. Okay. So if you consider that UK is the amplitude of the spin wave of wave vector k, then actually this second term represents the excitation energy, because this first term is the ground state energy of the system, and when the system is excited, then the total energy will be equal to energy in ground state plus excitation energy. Okay. So this first term actually represents the ground state energy. So definitely this second term is the excitation energy of a spin wave. So in this way, if you consider the spin wave of amplitude UK and wave vector k, then the excitation energy of a spin wave, if denoted by the symbol Ek, that will be equal to 2Je times n times Uk square into 1 minus cos of Ka. Okay. So in this way, we have obtained the expression for the excitation energy of a spin wave having amplitude UK. Okay. And now we will put the value of UK square from this equation A1. See, this is the final, this was the final result. UK square is defined here. This is the quantization condition for a spin wave. So when you will substitute this expression 2s times nk over n instead of UK square in that result, what will be then the value of excitation energy Ek? You can see this will be in fact 2Je n times UK square. Okay, see here 2Je n UK square times this much. Okay, so 2Je n is at age, and instead of UK square we will write 2s nk over n and times the remaining factor 1 minus cos Ka. Okay, and so this n and this n will cancel out, and Ek is simply equal to 4JES times 1 minus cos of Ka times nk. Okay. Now remember the dispersion relation which you have learnt in the previous lecture, in the first part of the lecture on a spin wave. So I have written that dispersion relation particularly in the case, sorry, not particularly, but in general, the dispersion relation which we have seen in the first part of the lecture, this is like this: 4JES times 1 minus cos Ka is equal to h bar omega. So here you have to remember this relation. This was the final result of the first part of the lecture. Okay, and we need the use of this expression here. So you must remember it. So from the dispersion relation, you can write that 4JES times 1 minus cos K is equal to h bar omega. Okay. So when you will use this result in the expression for this expression for Ek, then instead of this 4JES times 1 minus cos Ka, we can write h bar omega. So finally Ek is given as nk times h bar omega k. So you can see this energy Ek is also quantized. What will be the value of this Ek? You can see this depends on nk, and nk is integer. This can be 1, 2, 3, 4 and so on. So you can see that this energy is also quantized. Okay, and this result is actually just identical, okay, to the result which we have learnt in case of phonons in lattice vibration. So I have mentioned it here. You can see that Thus we observe that the energy Ek satisfies the same quantum condition as for phonons. Okay. The phonon energy is also quantized. Similarly, the magnon energy is also quantized. Ek is equal to Nk times h bar omega k. Okay. So in this way you can see that the different value of Ek, let us say E1k, that will be h bar omega k. Okay. When you will write E2k, that will be 2h bar omega k. Okay. So this Ek has discrete value, and so we can say that this excitation energy is also quantized. Okay. So this is all about the quantization of a spin wave. You have seen that the spin wave is quantized and the excitation energy is also quantized in the same manner as we have learned the quantization condition for the energy of phonons. Okay. So, and I hope you have clearly understand the idea which we have discussed in this present lecture. Now finally, in third part of the lecture, which will be actually the final lecture on this spin wave, I have told you earlier that the concept of a spin wave is actually very vast. So I have divided this lecture for simplicity in three parts. And in third part, we will learn about the thermal excitation of magnons and a very important and very famous law which is called Bloch 3/2 law, Bloch T 3/2 law, which is actually due to Felix Bloch, and we will discuss these two facts in our forthcoming lecture, which will be the third part of the lecture on spin waves. Okay, thank you very much.